All right, let's talk about one of the most powerful technologies out there today, machine learning. Seriously, it's the invisible brain behind just about everything, from what Netflix thinks you want to watch next to how a car can drive itself. It's a completely different way of thinking about how we build smart applications.
We hear the terms AI and machine learning all the time, and honestly, it can sound a little bit like magic, but it's not. So the real question, the one we're going to unpack right now, is how does a machine really go from being just a dumb box of circuits to making intelligent predictions? Let's pull back the curtain. So what even is machine learning? Well, to really get it, I think it helps to first understand what it's not. And to do that, we got to take a quick look at how programming used to be done.
See, the old way was all about handcrafting rules. If you wanted to build, say, a spam filter, a programmer had to literally sit down and write code like, if the email contains the words free money, then it's spam. You had to think of every single possibility. Machine learning just flips that whole idea on its head. Instead of feeding it rules, you feed it data. Thousands of emails that are already marked as spam or not spam, and you tell the machine, you figure it out. It learns the patterns all by itself.
And that is the absolute core of it. Machine learning is all about letting machines learn from examples, from experience, without someone having to spell out every single step. You're not giving it a detailed instruction manual. You're giving it a giant library of past experiences, that's the data, and a learning tool, which we call an algorithm. From there, the algorithm literally builds its own logic. It's a huge shift from programming the logic to programming the ability to find the logic.
Okay, so we've got the what, but how does a machine actually do the learning part? Well, it turns out there are two main strategies that cover most of what you'll see out there in the wild.
These two big approaches are called supervised and unsupervised learning. Just think of supervised learning like studying for a test with an answer key. You show the machine 1,000 pictures of cats, and each one has a label that says cat. It learns to connect what it sees in the image to that correct label. Now, unsupervised learning, that's totally different. It's like being told to organize a massive, messy library with zero instructions. The machine gets a bunch of unlabeled data, say a huge list of customer purchases, and its job is to find the hidden patterns on its own, like discovering that there's a group of people who only buy power tools on weekends.
Now, both of these methods rely on specific recipes, called algorithms. These are the engines that actually do the hard work of learning. And while there are hundreds of them, and some get crazy complicated, the basic ideas behind a couple of the most popular ones are surprisingly simple.
Let's start with one called K nearest neighbors. The motto for this one is so simple. You are who your neighbors are. That's it. To figure out what a new, unknown thing is, you just look at its closest neighbors. Let's say we want to classify a new data point. We just look at its, say, 5 closest neighbors, that's the K, and if most of them are blue, we guess that this new one is probably blue too. It's basically a popularity contest among its closest friends.
Another really powerful but simple idea is the decision tree. This is basically the machine learning version of a game of 20 questions. The machine learns to build a flowchart of yes or no questions to figure something out. Like, to identify a square, it might learn to ask, does this shape have 4 lines? If the answer is yes, it goes down one path and asks the next question, are the lines connected? And so on. The machine's job is to figure out what the best questions are and the best order to ask them in to get to the right answer as fast as possible.
Okay, so theory is great and all, but let's make this feel real. We're going to walk through the actual steps of building a simple model right now, just to see how all these pieces fit together in practice. Our mission, should we choose to accept it, is a classic in the machine learning world, classifying iris flowers. So we've got this data set of 150 different flowers. For each one, we have some measurements, like how long and wide its petals are. And, importantly, we also know the correct species for every single one of those 150 flowers. Our goal is to train a model that can look at the measurements of a brand new flower it's never seen before and predict which of the 3 species it is.
Now, right out of the gate, we have to do what is arguably the single most important step in this whole process. We have to split our data. We absolutely cannot use all 150 flowers to teach the model. Why? Because then we'd have no way to know if it actually learned anything or if it just memorized the answers to the test. So we're going to take a big chunk of our data, about 75% of it, and set it aside for training. This is the study material. The model gets to look at the measurements and the correct species for all these flowers and start figuring out the patterns.
And that other 25%? We lock it away. We pretend it doesn't exist. The model is never, ever allowed to see this data while it's learning. This is the final exam. It's how we'll get a fair grade on how well it can handle brand new, unseen information. So, the training process kicks off. The algorithm just chugs away on that 75% of the data, building its internal logic. It might learn a simple rule, like, hey, if the pedal width is super small, it's almost always a setosa, or it might build a whole complex decision tree using all the different measurements. So, training is complete. The model is feeling pretty confident. It thinks it knows the difference between these flowers. But now comes the million-dollar question. Can it actually apply what it learned to data it has never ever seen before?
This quote right here gets to the absolute heart of why we have a test set in the first place. The goal is not to be perfect on the data the model already studied. I mean, that's just memorization, right? The real goal is to be useful on new data. If a model just memorizes the training data perfectly, we call that overfitting, and it's basically useless for predicting anything in the real world. So, the time has come. We take our secret hidden test set of flowers, we show the model their measurements, and only their measurements, and we ask it to predict the species for every single one. Then we compare its answers to the real answers we've been hiding all along. And the result? 97% accuracy. That's a huge win. It means our model correctly identified the flower species almost every single time on data it had never encountered before. It didn't just memorize the answers, it actually learned. But that brings us to one last, and maybe the most crucial question of all. 97% sounds amazing, right? But what about that 3% it gets wrong? For classifying flowers, who cares? A mistake has basically zero consequence. But what if this was a model diagnosing cancer, or a model telling a self-driving car whether to brake or not? In those cases, that 3% error rate could be absolutely catastrophic. And that's the real takeaway here. Knowing a model's accuracy is just the beginning. The real work starts when we have to understand and plan for the consequences of its mistakes.